So good afternoon, everyone. Thank you for joining today's webinar. My name is Lexi Savick. I'm a sales coordinator at Terabee. Just so you know, we are recording today's session so that we can make it available to you afterwards. Today we are going to be discussing the basics of time-of-flight technology, and presenting will be Jan Koberman, who is our Chief Technical Officer here at Terabee.
Good afternoon, everybody. Thank you, Lexi.
Yes.
Let you start with a little introduction of Terabee, and then I take over.
Perfect. So I'm going to give a brief introduction, but I promise that Jan is going to grace us with his expertise for the majority of this presentation. So just so you know, we do have a Q&A tab down in the right-hand side on the corner. So if you have any questions, put them in there, and at the end we'll have a Q&A session so that we can get those answered. If you want to go to the next slide. So just, oops, back one slide. There we go. Just a little bit about us. We're a sensor and sensing solutions company. This is our core expertise. So we have three main areas, which is time of flight that we'll be discussing today, IR thermopile, and ultra wide band. Next slide, please. There we go. So this technology manifests itself in a range of products that we provide. We have sensor modules that are based on our time-of-flight technology, and then we offer various solutions in level monitoring, smart building, Industry 4.0, and mobile robotics. Next slide. And you can find out more about these products, their technical information, different use cases, as well as resellers that we work with, all available on our website, and you can also find our contact information there as well. So feel free to take a look after the session if you're interested. And that's all from me. So Jan, I'll let you take it away.
Thank you very much, Lexi. So today I'll tell you a little bit about time of flight. So since it's always very difficult to know what kind of audience will be in a webinar and what level of expertise I have, we decided to make this webinar relatively basic. So we'll talk more about the physics of time of flight, about the idea behind the difficulties, and you will see quite a lot of numbers. So we like numbers, not only the commercial department, but of course also in the design department. And I hope to get you a certain feeling for the numbers which are behind and this technology, and also the advantages, disadvantages at the end. I'll try to be quick so we can have a good session afterwards to discuss questions. So at that point, you can feel free to ask whatever kind of time of flight related questions, detailed or not. I'm open to that. So we usually talk about TOF. TOF is an abbreviation for time of flight. And in our case, we are talking about time of flight of photons, so light. Of course, you might have seen other technologies, for example, ultrasonic distance sensors. This is the time of flight of sound waves. Okay, so a bit of introduction to photons, speed of light, to get you a couple of ideas. You know, you have probably seen already the electromagnetic spectrum. It starts from radio waves or even lower. It goes via the visible spectrum, so all the light you can see around with your eyes, and goes to X-rays and all the way forward. It's just a question of energy your photons have. So what we do is we see our world in the visible, and our sensors actually work not too far out. It's near infrared, so it's light our eyes can't see, but it's not very difficult. It's not very different from visible light, meaning this is already a good advantage of time of flight sensors, especially when it comes to cameras, multi-pixel devices. What you can see with those cameras corresponds quite well to what you can see with your eyes. You know, this is a good advantage if you compare it, for example, to radar sensors, which work at frequencies, you know, which are much, much lower. And so in the microwave or even in the radio range, and the resolution is different. So you see the world in radar different than in the infrared. So that's why the time of flight in near infrared has this advantage of being more intuitive in its results. So photons. What are photons? So photons travel at the speed of light, which is about 300,000 kilometers per second. It's quite difficult to imagine, but we'll get to a couple of numbers. They carry energy. Each photon carries energy, and they usually do not come alone. Sometimes they come alone, but it's very rare. So you might have seen in our product portfolio, we have a sensor which is called the TR-Ranger Evo. It's one of our flagship single-point time-of-flight sensors. And to give you a feeling how much photon it emits, or made a little calculation. And at the end, you get up to 2.4 10 to the 13 photons, which is, let me see, 24 trillion. Lexi, remind me if that's correct. It's a billion trillion, because in German it's a bit different, but it's a trillion photons, which is, you know, another quite difficult to imagine number. But we'll come back to that because
Yes, trillion.
trillion, you're right.
Yeah.
So okay. So another important part to time of flight is the speed the photon travels. So 300,000 kilometers per second, as I said, it's a difficult to imagine number, but a couple of numbers give you a feeling. So the light travels about 8 minutes from the sun to the Earth. Okay, from the Earth to the Moon, 1.3 seconds. No, you know, still you can get it. From a geostationary satellite, 36,000 kilometers above us, it's only 0.24 seconds, or a quarter of a second. We are not too far away from the Mont Blanc here at Terabee, which is one of the highest mountains around. It is about 260 microseconds. Well, that's already difficult to capture. And as a rule of thumb, what you can say is the light travels about 30 centimeters per nanosecond. Or for the Americans, it's 1 foot per nanosecond. Not sure if it comes from there. I don't think so, but you know, it's easy to remember. So back to time of flight. What we measure then, you have all the ingredients now. What we measure is the time the light, a photon, travels, you know, after sending it out from a time of flight sensor to the target and back. That's why we have the speed of the light. We multiply it with the time we measure. We divide it by 2 because it's going back and forth at the end. Okay, so it's a round trip time we are measuring actually. So here we come now to the main ingredients of a time-of-flight system, which you have to take into account when you design a system or an application. Okay, first of all, sensor. Actually, it's the last thing you take when you design a time-of-flight system. First, you look at what you have as a target and what is the environment. So the target. Target can be lots of things. You know, everything you see around in your environment has a certain degree of reflectivity. So reflectivity meaning it sends the light, it receives back to you, either by spreading it or either by directing it away. You have two extreme examples, which is a specular reflection or mirror reflection. You know, when a photon comes in, it is reflected into a very specific and defined direction. While in contrary, you have the diffuse reflection, where a photon comes in and it's reflected back into a sphere of different directions, and it's randomly, you can say, scattered into these kind of directions. And you have all kind of mixtures. So unfortunately, in real life, usually surfaces are kind of mixture. So when you want to use a time-of-flight sensor, look first at your target. And by eye, as I said, the eye can already give a good idea about what is happening with time-of-flight signal. And keep in mind that a sensor which wants to measure distance needs to actually receive a couple of photons which it has sent out. So if you want to measure the distance to a mirror, yes, it works, but only in one very specific direction. So sometimes a diffuse target can be a better choice than a mirror target. Even though with mirror you get more photons back than with a diffuse target, it still gives you only a reflection if it's aligned in a certain geometry. And then you can have all kinds of situations in between. So this is actually something to keep in mind. Yeah, always think about, you know, how do I get my photons back to the sensor, and if it's actually possible. Here we have two extreme examples of reflectivity on the left. This is you know, typical aluminum foil, specular reflection. you can direct your beam of light away wherever you want. You will never get a signal back. Or you have something which is very low in reflectivity, then you don't care anymore if it's specular or diffuse. It just doesn't send any light back because it absorbs everything. This is an example. It's a painting called Vanta Black. It's actually a patented, pretty interesting kind of coating, which is very, very dark. So measuring to these ones will be tough, but you don't meet those very often in reality. So how is your target shaped? So your target can have different kinds of shape, different kinds of surface irregularities, and so on. So assume on a single point sensor, you send out a beam of light, which has a certain size, and it might actually happen to arrive at different distances, as you can see here with beams A and beams B. So what you will measure in this case is in a single point sensor, as with this one, you will get something which is somewhere in between. So you get a kind of averaging over the surface. You can also have situations where you get a so-called multipass effect, where some of the photons which are reflected back from your target, actually they bounce from another surface. So this can be, for example, a pipe, or very often customers come to us and say, okay, can I put a kind of cone or pipe, or can I measure the height of water or liquids in a pipe? And then you can encounter these kind of effects. So you want to make sure that this is not happening. So you probably choose something which is a bit wider, a cone which is wider or has a certain opening angle. Definitely, in all these situations, when you come to us, we can help you. Okay, you tell us what the situation is. We help you on how to use the sensor and what you can expect and what you cannot expect. Okay, small excursion on light propagation. So there are two extremes. So there is a laser which has quasi no divergence. Okay, it has a little bit, but you know, in our applications, or compared to our applications, it is very low. Or you have a so-called isotropic emitter, which is something which emits onto a surface. So on the surface, which gets bigger the further away you are from the sensor. Our TR-Ranger Evo actually emits somewhat in between those two. It's not a real laser, it's LED based, and it has a little divergence. This has advantages. So for example, what we see in applications, if you want to detect, for example, a cable hanging from somewhere in front of a background, or even a tree in winter where you have a couple of branches. So with a laser, you have a good chance to shoot next to it and not to get it. With a kind of more diffused beam, you have a good chance of getting some photons back and detecting it, for example, in anti-collision applications. So to give you an idea, to put the 24 trillions from the beginning into perspective, I did a couple of calculations to show you how many photons actually come back based on certain targets, okay? So the number is actually quite low. I won't go through every little detail here, but it will give you an idea. So our Evo 16, you have a target at 10-meter distance. The target is a mirror. Of course, it needs to be perpendicular to the beam, so otherwise you'll send the photons back somewhere and not back to the sensor. So it's specular reflection, pretty much the best situation you can get. And what you get back is actually only 0.016% of those 24 trillions. I'm not going to do the math now, but you know, you get the idea. So let's get to something more realistic. Point number 2, our Evo sensor target distance 10 meters, and the target is an 88% Lambertian or specular, sorry, not specular, diffuse reflecting surface, which you know, is typically a white wall. Okay. So what you get back at that point is you know, a factor, let me see, 100 less than compared to a mirror. Okay, 0.00014%. Okay, and to get even worse, let's go to 60 meters in the same configuration. And then the number is so small that I don't even know. It's probably 0.39 millionths of a percent. And then out of those 24 trillions, the number of photons which come back is actually only a couple of 100,000. So, which is not a lot. Another ingredient to time-of-flight measurements is the environment. So indoors, typically, the environment, you don't care much. Most lighting systems you have these days are LED-based, fluorescent light-based. Incandescent light is dying. So typically, no indoor lamp has an infrared content, meaning there's no light which could disturb or saturate a time-of-flight sensor. Because what can happen is that you have your light which comes back from the target, so the light you send out, but you will have an additional light at the same wavelengths which falls onto the sensor. So sun is a so-called black body emitter. So when you go outdoors, you will have sunlight, not every day, but you know, a nice sunny day, you'll get quite a lot of sunlight. And it can happen that it falls onto your sensor and saturates the sensor, at which point it cannot measure anymore. What we did is we decided to go for wavelengths which has actually a little dip in the spectrum of the sun, 940 nanometers. It is actually attenuated by the humidity, which is in the atmosphere. So this helps already to keep the saturation level low. And you will also see a difference between sunlight at noon or sunlight in the afternoon, because it will have a different kind of path that travels through the atmosphere. So the infrared content goes down quicker than actually the visible light content. So at some point you will see that in the afternoon your sensor will actually be more performant than at noon. So you have to take this into account when you design your application. And a question which comes up quite often is fog and rain. So you have to imagine that fog and rain is actually material which is in the path of the light. It has the path the light has to travel, meaning it can absorb the light or it can scatter it away. And it can severely impact the performance of a sensor. So snow, for example, is difficult. Rain, not that much, apparently, which is quite interesting. Fog, there's an interesting cutoff you can see at some point. When the fog gets too dense, it starts falling quite quickly. But this is also something which you have to see, and you have to take a certain margin of emitter power, or you select the sensor accordingly if you expect to have fog or rain in your application. Okay, so this is the basic overview of time-of-flight sensors. I hope it gave you a good idea about the numbers we are dealing, and the first idea of what you have to look at when you design an application with a time-of-flight sensor. So now that's good time for question and answers.
Yes, thank you, Jan, for that presentation and the introduction. A reminder, if you haven't already added any questions that you have, you can add them directly to the question and answer or the chat function on the right-hand side of your screen. So feel free to do that. We do have a couple, so I'll go ahead and get started with those. And as you add them in, I'll read as many as we have time for. So the first one is, what are the advantages of time-of-flight sensors compared to ultrasound sensors?
So one of the biggest advantage is that you actually have a more concentrated beam. So a time-of-flight sensor, you can have laser-based time-of-flight sensors where you have this kind of non-dispersing beam, or zero divergence beam, or pencil beam, where you actually scan just a single point, or a slightly bigger scan surface as we have with the LED-based sensors. And you can operate in areas which are confined, so indoors, and you won't get any kind of multi-reflections, echoes, and so on you typically get with ultrasonic sensors, and you definitely get a better resolution if you start scanning with such a sensor. So for example, a sensor mounted on a moving robot, if you know about your position of your robot, you can actually with a single beam move your robot and scan your environment, which is something you cannot do with an ultrasonic sensor because the beam is just too big. Also with time-of-flight sensors, you typically get a better range than with ultrasonic sensors. But okay, this is dependent on the device you choose. But you know, in let's say in range per money, time-of-flight, optical time-of-flight beats the ultrasonic.
Okay, great. Looks like we have another one. Is the EVO 3 meter more resistant to high illumination than other sensors in the EVO range? It's talking about our Terabee sensors.
Okay, so it always depends what you consider as being illumination resistant. So in principle, you get a little bit better because you have more margin on that sensor than compared to the high range sensors in terms of optical power versus detection efficiency. But usually what we say is it's better to look into the use case and the application before creating a false expectation. So with time-of-flight, you need to gather certain expertise when looking at the application to know what to expect from sensors.
Okay, great. And then we have another question from Yan. It says, how are the performance impacted when measuring distance over water? And do you have any experimental data about this?
Over water means distance from a sensor to a water surface, like a water level. Is it that? So yes, that
Yes. Yeah.
yes. Okay. So we have done quite some experiments on this. It typically becomes very easy if the water has a little bit of movement, because depending on the movement of the water and the angle, you get a quite good reflection. So water is quite reflective in that sense. Our sensors are not polarized, so we do not have issues with polarization, which can change the amount of absorbed photons depending on the angle you have impacting on the water surface. We recommend mounting the sensor perpendicular to the water surface. And then in most cases, so with clear, fresh water, we got a pretty good result out of it.
Okay. He says thank you. So it sounds like that answered his question. Great. We have another question here. What is the advantage points with respect to stereo vision technology? And that's from Chris.
Okay, stereo vision technology. Now we are talking not single point, we are talking multi-point, multi-pixel time-of-flight. I mean, both technologies definitely have their advantages and disadvantages. What I can say, time-of-flight is the choice when you expect to have environments which have either no features. So stereo vision relies on the fact that you have two cameras which detect the same feature in the environment. If you have a clear white wall, you will not get anything. Okay, so at that point, the time-of-flight camera is fully an advantage because you will get still one measurement per pixel. So if you have few features in a stereoscopic camera, is you get about an amount of measurements is about the amount of features you can detect in the image. So there you have to be careful. If you buy a stereoscopic camera and you say each camera has something like 10 megapixels, doesn't mean that you get 10 megapixels of distance data. Okay, it depends on what you are looking at. While when you buy a VGA time-of-flight camera, in most cases you get also the VGA amount of pixels, 640 by 480, except of course if in the field of view of the camera you have areas which are either so absorbing that no photons come back, or so reflective that the photons get, directed away from the camera. Also, time-of-flight cameras, they are not dependent on the ambient illumination. Okay, actually it's the opposite. If you have too much ambient illumination, you might get into saturation effects. While in darkness, they work very well.
Okay, great, thank you. A follow-up question, do you have any experience also so-called active stereo vision of Intel's D435?
Okay, so I think there's many. Apart from the fact that I think Intel discontinued to make those, the active stereo vision is actually a combination of stereo vision plus projected light. So what people do, it's not only Intel, there are other people who do projected light systems, is they project a pattern of light in the infrared, so you can't see it by eye, onto the object, the target you want to measure. So the camera, which is infrared sensitive and also only looks in infrared band, will see this pattern and it will see the deformation of this pattern. And this deformation of this pattern can then, by calculation, convert it into distance information. So this is computationally intense. And again, it depends, your resolution doesn't depend on the number of pixels you have on your camera, but the number of points which are recognized on the target and projected on the target. So still, stereo vision and projected light, be careful when you see, oh, it's using 5 megapixel cameras. You won't get 5 megapixels of distance information. You might in certain application get more pixels than you need. Okay, that could be totally fine, but there might be other applications where it just doesn't work. Also, the structured light is slightly more sensitive to ambient light, so it saturates a bit more in outdoor conditions. But okay, this is a bit dependent on the model, but it's a general feeling.
Okay, he says thanks. We have another question. Have you seen emerging integration complementary techniques for combining other sensors for range and altitude, given the pros and cons mentioned on time of flight?
For which, so range and altitude, we are probably talking about UAVs, aviation, so right? Is that the sector?
Yes.
Okay. So actually, a bit of history. Terabee started in that area, but we are not working too much anymore actively in the research in UAV. We're still promoting sensors for these kind of applications. So yes, you can have radar sensors for ground distance ranging, also for anti-collision. So probably quite good sensors to do so. Nevertheless, there are sensors which need more resolution, ground resolution. A good example was a ground distance measurement for the use in cornfields. So you point your sensor down, and with the time of flight, you get actually two distinct points where your measurements are in. So basically, you have the soil plus you have the top of the crop, and you get all the values in between, which can help you to identify where you are. While with radar, I think you will probably more get the soil only. So combination of multiple sensors, sensor fusion, as it's called, makes sense, but you have to look into the final application to actually decide if it makes sense to invest on it or not.
Very good. That was helpful. Do we have any other questions? I don't see any so far. All right. Well, in that case, that brings us to the close of our session. We are going to be launching a poll, so you might see that appear on your screen. If you could just fill out the information at the time. Thank you, Jan, for the presentation, and thank you everybody for participating. We will follow up with you guys via email with the recording, and then also keep an ear out for future webinars. And yes, if you have any questions after the fact, don't hesitate to get in contact with us. We're happy to discuss with you further on this topic or other topics. And we look forward to seeing you at the next webinar.
Thank you, Lexi. Thank you, everybody. Have a nice afternoon.
Thank you. And the link to the poll just got added to the chat. So
Great. Bye-bye.
have a great day, everyone. Thank you. So